This video is going to look at how to do analysis of variation by hand. This is the process for comparing several averages. So suppose in this problem, I'm looking at how much Amelia, Barbara, and Cynthia make in tips. If someone didn't tip, they got a value of 0 there. Average of $12.50, standard deviation of $3.50, and an N of 80 for Amelia. 1550, 325, and a sample size of 50 for Barbara. And Cynthia has an average of 10.5, standard deviation of 3.75, and an N of 70. Test if the averages are different. ANOVA is always a test, so it's going to have the same 4-step process. First step is I'm going to have my hypotheses. My hypothesis for the null is that the average for Amelia, Barbara, and Cynthia are the same. Alternative hypothesis is at least one average is different. Now, just as a note as I'm getting started here, it won't tell me which average is different. So I'd have to do follow up either 2-sample t-test or 2-sample t-ints to figure out which group is different out of the set. Maybe A is different than B, or A is different than C, or B is different than C. So I would have a lot of follow-up tests to do. So a question might be, well, why would I even want to do ANOVA if I'm going to have so many follow-up tests to do? Well, if I fail to reject the null hypothesis and I don't have evidence of a difference, I wouldn't do those follow-up steps. So ANOVA pretty much tells me if I have a lot of work ahead of me or a really small amount of work ahead of me. It's kind of like a pre-test test. So step 1, I have my hypotheses, my null, and my alternative. Step 2, I'll have my model. My model will be the F distribution. My F distribution looks at the difference between a mean square of a treatment and a mean square of an error. I will show you how to calculate these things. It has 2 different degrees of freedom because I have 2 types of variations I will be analyzing. That's where the name analysis of variation, or ANOVA, comes from. The degree of freedom for the numerator will end up being k minus 1, where k is the number of groups. And the denominator is capital N, that's the total number of terms, minus k. My 3rd step will be p-value. My 4th step will be conclusion. So let me talk about the 2 types of variation that we're comparing. We're comparing variation within our groups and variation between the groups. So the variation between groups compares the averages to some overall average. So what this is doing, just as like a rough picture here on the side, is suppose I have all of these groups and I'm imagining that I made box plots for Amelia, Barbara, and Cynthia. This doesn't actually match those values. It's just a super rough sketch of conceptually what's going on. I want to compare each of these averages to sort of an overall average of all the values, a capital X bar. So I want to compare how close each box is to the center. This will tell me my variation between the groups, but I also want to know how big the boxes are to see if those boxes overlap. That's the variation within. So I'm comparing how far apart the boxes are and how big the boxes are. I need to find an overall average as this center line to do this comparison for the between. This capital X bar, I would find this by taking all of the values, adding them up, and dividing them by the total number of terms if I had the raw data. If I don't have the raw data, this is just a weighted average. Here's what I mean by that. Amelia had an average of 12.5, and she had this for 80 people. Barbara had an average of 15.5, and the weight for this was 50. And finally, Cynthia had 70 individuals with an average of 1050. So when I multiply these numbers, 80 times 12.5, This is the total amount that Amelia got in tips. When I do this 50 times 15.5, this is how much Barbara made in tips. 70 times 10.5, this is how much Cynthia made. So in total, they made this much money if they pooled it all together. And if you're pooling it all together and you're wondering how many people they all served, well, I have 80, I have 130, I have 200 tables that they looked at. So this divided by 200, on average, they got $12.55 per table. So that's what that would look like if I pooled it together. That's what this capital X bar does. It pools together all of those values. So my variation between groups, or the mean square of the treatments, because if this was a medical thing, this is comparing treatments A, B, and C. In this case, I'm comparing people A, B, and C, but I'm looking between the groups there. I'm going to have a weighted average for these differences. So I'm going to have the number of individuals in the first group, so that's 80, times the average of the first group, that's 12.5, minus the overall average, that's my 12.55. So this is telling me that Amelia is really, really close to that center line there. I'm going to add these up vertically just so you can see the pattern, but I'm going to put parentheses over this whole set and do some division as well. The next person was Barbara. Barbara has a weight of 50 tables. Her average was 15.5, and I'm going to compare that to the overall average of 12.55. So Barbara was considerably further away, but she also served less tables, so that might be a factor in that. Maybe this is just due to sample variation. Finally, Cynthia looked at 70 tables, an average of 10.5, and I'm going to compare her average to the overall average of 12.55. So what I'm doing here is I'm looking at the sum of the squares of all of these different treatments. This is called the SST so far. And I want to average this out based off the degree of freedom for the groups. Well, if I have 3 people that I'm looking at, my degree of freedom should be 1 less than the number of groups. I should have a degree of freedom of 2. In general, your degree of freedom is going to be the number of groups minus 1. Our number of groups for this problem is 3. I'm looking at 3 people. So my denominator is going to be 2. I'm going to type this into my calculator and see what I get for my mean square of the treatment. In other words, my variation between groups. It's labor intensive, but that's okay. 80. Amelia. Barbara. Cynthia. I'm taking this whole quantity and I'm dividing it by 2. I have an MST of 364.75. So when I'm trying to find the F ratio, this will be on the top of that fraction. You can think of this as sort of the variation that's taken up by the groups. Now I need something to compare this to because I don't know if 364 is a large number or a small number. That's what the mean square of the errors does. It takes the total of all of the degree of freedom for each of the individuals times the standard error squared. So I'm looking at the sum or the standard error squared, and I'm going to average this out based off the total degrees of freedom. Let me show you what I mean by that. I'm going to start with Amelia. This is based off of the inside spread. While Amelia had a standard deviation of 3.5, so her variance was 3.5 squared. She served 80 tables, so her degree of freedom is going to be 79. I'm going to line these up just so I can see each of the people. Next person was Barbara. She served 50 people. That gives her a degree of freedom of 49. Her standard deviation was 3.25, and I square that. So I'm looking at a sum of the squares of the errors, an SSE. Next individual, 70 was the number of samples, so they have 69 for the degree of freedom for Cynthia. And her standard deviation was 3.75, and I'm squaring that. I'm going to divide this by the total number of values. So if I added all of the tables up, I had 200 tables. Minus the number of groups, I have 3 groups. Now, just a note here, I want to show you what's going on. If I do 79 plus 49 plus 69, this gives me 197. So if I added up all these degrees of freedom, I get 197. If I do 200 minus 3, I also get 197. So what I'm actually doing here is I'm taking all of these standard deviations, I'm squaring them to get a variance, and I'm kind of averaging them out. So I'm finding the pooled variance when I do this variation within. I'm averaging out each of these variances. So I'm going to type this into my calculator. .25 squared is the same thing as if that square is on the inside or the outside. I don't even need parentheses here. I'm just trying to show you the difference between the degree of freedom and the variances. And I get 12.465 or so. So my MSE a good way to see if this is reasonable or not reasonable is if you take the square root of this number, I get 3.5. That is about the average of all of these standard deviations. So your number that you get for your MSE, if you take the square root of it, it should roughly give you what that pooled standard deviation looks like if you were to treat this all as one big group. So this compares all of the averages. This compares all of the standard errors. You can think of the MST as the amount that you've spent, and you can think the MSE is sort of like your bank account. So I had $12.46, and I went out and I spent $364. I spent way more variation than I was allowed to. That happens when my averages are drastically different. If I spend less variation than I'm allowed to, then this tells me that these things are really close together, and then I'm probably going to fail to reject the null hypothesis. Those things will be pretty close. So in general, you're going to have a small f if all of your averages are close to each other. And you're going to have a large f if they are really different. When I say small and large, I'm thinking of the f kind of as a percentage. So in my head, compare to roughly an f of 1, just to get a little bit of number sense. So let's calculate RF here and see if this is large or small. I'm taking my MST, that was 364.75, divided by my MSE. So I have my variation between the groups divided by the variation within. And when I type this into my calculator, I get 29.26. That's way bigger than 2. This is a massive F ratio. So I'm almost certainly going to notice that the averages appear to be different. I'm almost certainly going to have a small p-value where I reject that null hypothesis. In my calculator, this will always be a right-tailed test. I'm going to have p-value is f-CDF, whatever my F ratio is, comma infinity. So I'm looking at this much spread or more, comma, it will ask for 2 different degrees of freedom. It wants the first degree of freedom. That's your first denominator here. So the denominator for my numerator was 2, k minus 1. And it'll ask for your second denominator. That's your capital N minus k. So for our setup, I have f-CDF. My F ratio was this 29.26, comma infinity. My first denominator was this 3 minus 1 number, was 2. My second denominator was this 200 minus 3, was 197. If I'm trying to find F in my calculator, on the TI-84, I go second vars. And then I'm going to scroll until I see f-CDF. This is the same spot where I found chi-squared CDF and t-CDF. I type in my ratio. So my ratio was 29.26. It's always a right-tailed test, so I'm going to type in infinity, a really large number there for the upper. My first degree of freedom was 2. My second degree of freedom was 197. And this gives me this E minus 12 is scientific notation, so that means I'm going to have 11 zeros and then a 7. This is really, really small. 7 times 10 to the negative 12. We'll just call this 0 plus, it's so small. In the TI-89, I am going into apps and then stat list editor. I'm going up top for distribution, so F5. And I'm choosing the f-CDF. I have my 29.26 value for my lower. Upper is infinity. My first degree of freedom was 2, that's k minus 1. My second one was 197. That's the total number of terms minus the total number of groups. And this gives me, as before, 7 times 10 to the negative 12. It's giving me this 0 plus p-value. Finally, in GeoGebra, when I open up GeoGebra, I go into the option on the side that says probability. And for distribution, I am working with F. My first degree of freedom was 2. My second degree of freedom was 197. It's a right-tailed test, so I'm going to choose this option so it's shaded to the right. I typed in my F ratio, 29.26, and then this will spit out my p-value. It's so small this time that it's just giving me a number of 0. That's fine. I have 0 plus. Conclusion, if your p-value is low, it's pretty low, your null must go, so I would reject the null hypothesis. If you're rejecting the null hypothesis, this means that you have, or we have, evidence that they do not all earn the same amount on average for the tips, for Amelia, Barbara, and Cynthia. So if I was wondering, okay, then, which person got the most for tips or the least for tips, or where are things different? Well, that's where I have to go back and start to compare these things one at a time and compare Amelia and Barbara to see if there's a statistical difference between those two people. I'd have to compare Amelia and Cynthia, and I would have to compare Barbara and Cynthia. That's a lot of follow-up tests that I was hoping to avoid, but unfortunately in this problem I rejected the null hypothesis, and that tells me that there is something going on, so I would want to investigate what that difference actually looks like. Again, ANOVA compares two types of distributions. First type of variance that I'm looking at is the variance based off of the centers. The second type is this variation based off of the standard errors. This gives you a ratio. If your ratio is bigger than 1, that's usually pretty large and you'll end up with a small p-value. If you have an F ratio smaller than 1, that's usually so small that you would end up getting a large p-value and you would fail to reject the null hypothesis. But the way I looked them up in my calculator is by using this FCDF function.